Let's look at our next section, everyone. Section 6.2, volumes of revolution. So I want you to imagine that you've got a curve called y equals f of x, and you're going to rotate this curve about the x-axis. So can you imagine I'm moving my fingers, right? You're going round the x-axis. If you did that, do you know you would create a solid that would look something like this? A bit like a solid vase. Some of them look like bells when you do it. Others look like fish, whatever you want to call it. But we can find the volume of this shape. It's called a volume of revolution. Right? It's a shape that you get by rotating something, right? Or rotation about the x-axis in this case. And the formula is remarkably simple. The volume is the integral, so we use integrals, of course, from a to b, from start to finish, pi, the function, squared. And for those people who do not like magic, I'm going to try and sort of approve this formula to you. It's only so that for some people it just helps if they can see where this weird formula came from. So I want you to imagine I took this shape. You don't need to write this bit down if you don't want to. You can always watch the video at the end. You probably do want to write this bit down. Now I want you to imagine that I take a tiny little strip here, and that strip is going to be delta x wide. If you did that cut and you looked at it from this side, can you imagine what you would see? I wish I was an artist. Wouldn't it be a disc? Like a coaster called a disc. And the x-axis would pop out the center. Now, what's the volume of this disc? Well, it's pi times the radius squared, that's the circle part, times delta x, right? Circle, pi radius squared. Now, if you take that distance and you go vertically upwards, which is essentially from there going vertically upwards, isn't this distance the height of the function at that point? So your function becomes pi f of x squared delta x. And then you imagine you add all those strips together. And that's a Riemann sum. But Riemann sums, that turns into an integral. And that turns into a dx. So do you see the connection between Riemann sums and integrals? And so there is your proof that the volume of revolution, when you rotate something about the x-axis and it's a single curve, is that guy. So we are going to find some volumes now. I think there's only about 7 questions, so there's not an awful lot of these, so I don't want to use up too much of the good stuff. I'll just do a square root of x. So, square root of x looks like that. Starting at 0, finishing at 4. So, can you imagine you rotated that shape about the x-axis? It would look probably something like that. Bit like an acorn. Would that look? To me, that kind of looks like an acorn. Right. The volume is the integral of pi f of x squared dx from a to b. Now, one of the things I do just to make my life easy is I typically pull out the pi. You're allowed to do it because it's a constant. The integral from 0 to 4, the square root of x squared dx. So whatever the function is goes here, and you square it. And the advantage of pulling this pi out is that if I get whatever this answer is, if it's 7, the final answer is 7 pi. And if it's 3/4, the final answer is 3/4 pi. If you keep it inside, it just gets awkward and it's in the way, and you end up writing it in lots of different places. You know, imagine it's a more complicated question, you write it all over the place. So just forget it. So that's going to be the integral of, oh God, you couldn't get much easier than that. X. Power rule. Add 1 to the power, divide by the new power. Okay, plug in 4. 1/2 times 4 squared. Take away 1/2 times nothing. That ends up being 8. So the volume of that acorn is 8 pi, and that's an exact value. Don't bother turning it into 3.14 and tell me it's 24.8. We just want exact value. So it's okay to have slightly weird looking answers because of that. Now, that was probably the simplest example of me finding a volume of revolution, but the process is going to be the same even when this f of x starts getting uglier, right? Bigger and messier. So far, so good. Any questions, or can we move on? Move on.
Could you technically rewrite that to just pi and then your function b over a f of x squared?
Oh, yeah, you could if you just want to. That would be the equivalent, which is what you just said, right?
Yeah.
Yeah.
Okay, thanks.
Nothing wrong with doing that. Seems fine. Are we good? Right. How about y equals the square root of sine x plus 1. And we're going to do x from 0. Oops, no way around. X is 0 to 5.2. Now, I guess I could plug that into Desmos, but as long as you're told the function and the start and finish values, you don't need to worry about anything else. You don't need to worry about crossovers or, you know, x-axis intersection. None of it really matters. The formula takes care of it all for you. So we can just go straight into the volume. Pi, the integral from 0 to pi upon 2. The function, which is that guy. And that's pi, the integral from 0 to pi upon 2. If you square a square root, don't you, essentially those two processes cancel out and you just get whatever's inside the square root. Can you see these questions work really well algebraically for square root functions? Right. Square root of x, square root of 2x plus 1, square root of sine x plus 1, square root of, insert anything you like. This particular question, doesn't the algebra work really well with them? Because don't you square that function, and squaring a square root pretty much takes care of itself. Pretty straightforward question, but still causes problems. So I want to ask it, what is the antiderivative of sine x?
Negative cosine x.
Correct. Easy to forget if it's plus or minus, right? The more times we pause and think about it, the less chance we'll have of making that mistake. Would you agree that the number 1 has an antiderivative of 1x? So let's see what we get. Plug in pi upon 2. Take away, plug in 0. What is the cosine of pi upon 2?
0.
Good. So that's just negative 0. So it's 0 plus pi upon 2. Take away, what's the cosine of 0?
1.
And what we get now is pi. Pi upon 2 take away 1. I'd probably just leave it like that. Would you agree that's quite a nice style point look?
Wouldn't it be
It
adding
is
one?
the same.
Because for cosine,
Take away,
well,
well, cosine
would
is
be
0 is
negative
1, so we're
cosine,
taking.
right? Negative cosine.
Well caught. I screwed up there. Thank you. It could be done like that as well. Well caught. I like that, but I don't see any real problems. Would you agree that's cool? Both are right. So far, so good. Right, let's do something that isn't a square root, just in case you think every question has to be. Let's find out what happens to that shape from 1 to 2. Oh, and I should have been writing these down. Rotated about the x-axis. Every question so far has been rotated about the x-axis. I just forgot to mention it specifically. Okay, now its volume is pi, the integral from 1 to 2 of f of x squared dx. Now, do you see that in these kinds of questions that don't have a square root, can you see that you may well have to do some more algebra before you can integrate? What do you think I'm going to have to do to this before I start thinking about doing any integrations?
Foiling.
Yeah. Now, you can check it later, but trust me, you get x to the 4, 2x cubed plus x squared. So we just take that as being true. Now, in this case then, aren't we basically just doing power rule, power rule, power rule, evaluated at x equals 1 to x equals 2. Okay, you plug in the first guy. It's 1/5 2 to the 5. That's essentially a half 2 to the 4. And 1/3 2 cubed. Take away. Do you know if you plug 1 in here, you just get the fractions left over? So I'll save some time and say 1/5, 1/2, add 1/3. And then I say, time for calculator. So 1/5 times 2 to the power of 5. Add 1/2 times 2 to the power of 4 plus 1/3 times 2 to the power of 3, and then hit the math button and turn it into a fraction. And all of this gives me 256/15. Take away these three guys. So 1/5, add 1/2, add 1/3. Hit the math button, choice 1, and get 31/30. And then lastly, 256/15. Take away 31/30. Hit the math button, choice 1, 481/30 pi. God, isn't it great that calculators can do fractions? Because I would not want to do that the long way. Are we comfortable with the process of evaluating at the two numbers and just letting the calculator take care of all the ugly stuff? So the volume of that shape rotated about that. I guess if I try to draw it, I'm not sure I could do a good job, goes there. At 1, it would be about here, so it would start there. And at 2, it would finish. It would be a pretty boring curve. It would be that curve there, rotated about the x-axis. It'd look a bit like a bell, which somebody lopped the end off. You don't need the pictures in these questions, which is kind of helpful, isn't it? At least it's one less thing that you need to do, because this formula takes care of it. Right, a couple of truisms. These are physical volumes. Even although we do integration to get them, the answer is a physical object. That means these answers must be positive. If you do one of these volume questions and you get -42 pi or something, you are just wrong. Go looking for where you screwed up. You can't even get 0, because if the volume was 0, wouldn't that essentially mean the shape wasn't there? So you know you're not even going to get 0. It's definitely going to be, 4/11 pi or 42 pi. The pi is kind of guaranteed because of the way the question works, right? So those are things that are just always going to be true. It must be positive. Right? It's going to guarantee that, and it's going to have a pi tagged at the end. Oh, my usual. Any questions yet? We're good. Okay. Then I am going to show you a piece of algebra to do with trig, and then I'm going to do a question where we needed that piece of algebra. So there are a number of different ways in which you can rewrite sine squared and cos squared. But the version I'm going to show you, the identity I'm going to show you, is the one that we're going to be using today on the next question. Sine squared x is a half 1 minus the cosine of 2x. And cos squared x is very similar, but it's got a plus instead of a minus. And the reason I'm telling you those two is that I'm now about to give you a question where we use one of these. So I'm going to pick a really simple function, sine x. And I'm going to do it from 0 to pi. So if you imagine sine x would look something like that from 0 to pi. And I'm still going to rotate about the x-axis. Could you imagine the other half like that? It might look like a sphere to you, but it's a bit more like a lemon. Can you imagine somebody got a sphere and kind of crushed it down a little bit? It's almost spherical, but it's not a perfect sphere. So it would look like a little bead, right? Now its volume is pi, the integral from start to finish of the function squared. We have the convention that when you do sine squared or cos squared for the matter, any trig function squared, don't we write it like that? Agreed? So you write sine squared. Now, I want to integrate that. This is where this kicks in. If I distribute this, which I should have probably done right at the start, then sine squared x is that guy. So this question now becomes pi instead of sine squared. I'm replacing it by that guy. Integrate a half, you get a half x. Can you remember the linear shortcut trick that I gave you on Friday? Right. Don't worry about the negative a half. We'll sort that out in a minute. What does the cosine of 2x get you when you integrate it using that shortcut trick? The cosine of 2x, what's its antiderivative?
Half sine 2x.
Yeah. Now I have negative a half of those. So you maybe not need the line I've just written in, but I put it in to try and show you where the negative a quarter came from. Right. Are you okay with the negative a half by another half, and that's why it's now negative a quarter? So the sine of 2x, sorry, the cosine of 2x gets you this, negative a half of this gets you that. Now we're ready to rock and roll. A half pi minus 1/4 the sine of 2x, which is 2 pi, that's the first one. Take away a half 0 minus a quarter sine of 0. Take away a whole load of zeros, essentially. What's the sine? What number is the sine of 2 pi?
Zero.
Right. So all of that is 0. So your answer is 1/2 pi squared. It's kind of elegant, isn't it? It's kind of nice, tight answer. Now, I haven't done it yet, so let's do it right now. And it will almost take no change to my working. Suppose I went and said, I want the whole kit and caboodle. I want this guy and this guy rotated about the x-axis. Now, what that would look like would be a very small necklace. Can you imagine 2 beads stuck together? 2 little pearls. Great. Now, what would the change? It doesn't care. The formula does not care if the thing that you're rotating is below the axis or above the axis. I would change that to 2 pi. That means this would be 2 pi, this would be 2 pi, this would be 2 pi, this would be 2 pi. And then plugging in 2 pi gets you 2 pi here. Plugging 2 pi in here makes you 4 pi. And the zeros are still zeros. But isn't the sine of 4 pi also nothing? So a half of 2 pi gets me pi. And the answer is that this 2 bead volume shape is equal to pi squared. A remarkably nice, tight answer. It's roughly about 3.14, 3.1. It's almost 10 cubic units, if you were imagine it as a value. Any questions about that, or are we good? Last chance. Moving on then. Volume of revolution, excuse me, about the x-axis using, excuse me again, the area between 2 curves. Excuse me. Try and show you what's going on here. want you to imagine that we start at A, and we start at B, and we have our function, y equals f of x, and then we have another function, oops, y equals g of x, and you see this fella here? This is the guy that's going to get rotated about the x-axis. So we are talking about finding the volume of a really weird shape. I'll try my best to draw it. It's about that much. Where's my green? Green's about here. That guy's about here. That guy's about here. Definitely going to screw this thing up. I'll try my best not to. It would look something like this. But going through the center of it. There would be a funny hole. Can you see the hole would be a kind of circular, like a, I don't know, like some worm had ate its way in a random path through the shape. Can you imagine finding the volume of such a weird shape? How difficult it might be. I'm not going to prove this one. I'm just going to tell you what the formula is. And maybe when I tell you the formula, you'll think, hey, that makes kind of sense. Can I pull out the pi? Because it's in the way. Oh, were you expecting the formula to be that guy? I mean, in a way, it kind of makes sense. Isn't it the volume of the big guy, subtract the volume of the hole? And this is like the volume of the hole, and this is the volume of the big shape, right? It's like take the bell and then cut out of it the green hole. Volume of big bell, take away volume of green hole. To me, that intuitively feels right. Okay. Are we good? Right. So let's show you a question where we find the volume of revolution using two curves, still about the x-axis. So if you can bear with me for a little while. And I'll pick something similar to the homework questions. Let's do, oh, that pen's gone, I'll throw it away now. Let's have my first function is going to be x squared, and my second function is going to be 2x. And I've just realized I shouldn't have done that. And the reason I should call them that and not this is, couldn't this one end up being the f of x and this one could end up being the g of x, right? So in Desmos, you would sketch the two curves. Well, I'll come to this in a minute. This is y equals x squared. And this fella here is y equals 2x. And the region that we're going to rotate about the x-axis is that banana shape. And so they describe it as the region enclosed by the two curves. So it's going to be called the region enclosed by the two curves. And there we go. So I know that guy is 0. This guy here, if I had Desmos and I pulled it up for you, you could actually click on it. And can you just trust me, it ends up being 2. Right, I got it from 9 The volume, pi. The integral from start to finish. Somebody squared, take away somebody squared, dx. So the only guy left is who goes as f and who goes as g. So can you imagine my little rectangle guy that looks like that? Now, when you do that, do you see the straight line is higher than the curve? Do you agree? The straight line is higher up, which means the straight line is him. And the curve is him. That makes sense? If you've got Desmos in front of you, you do your little vertical rectangle. The high up one is F, the lower down one is G. And the next stage is pretty much just making it look pretty before we integrate. 4x squared, subtract x to the 4. We're happy about that guy, take away that guy. Power rule, add 1 to the power, divide by the new power, add 1 to the power, divide by the new power, evaluated at 0 and evaluated at 2. It's going to be 4/3 times 2 cubed, take away 1/5 times 2 to the 5. Is it okay for me to just say take away 0? Can you imagine you get lots of zeros there? I'm going to let the calculator do the rest. So 4/3 times 2 to the power of 3, subtract 1/5 times 2 to the power of 5, and then math button, choice 1, and I get 64/15 pi. If I try to draw that shape, I'm not even sure it would look good. That doesn't even look very much like it. Can you imagine some I don't know what it would look like. It would look like some V-shaped vase. Right, if I turned it vertical, it would look like a vase with the interior being curved towards the point. Visually, that's not very appealing. But thankfully, you don't need to draw the 3D shape to be able to answer the question, right? Although I can visualize it, I can't draw it very well. Are we comfortable with what we did here? Are we good? Right, so there is another part to this that we won't be doing today, except to give you a quick intro to it. And that is we're going to look at rotating a shape about the y-axis instead of the x-axis. Right? So that's what's going to happen tomorrow. What I'd like to show you today is to prove to you what the volume of a sphere is. You might think, how am I going to do that? Does anybody here actually know what the formula for calculating the volume of a sphere is? It's not a kind of formula you would meet with every day, but you might know it.
What is it like? 4/3 pi r to the third, I think.
It is exactly that.
It's been a while since I took physics.
Right. Well, you know that that's magic. Don't we just tell you, you want the volume of a sphere? Here you go. Wouldn't you like to actually prove it? To actually find out how they came up with that? Right. So we're going to pretend that we are the first people in the universe to try and find the volume for a sphere, right? Nobody's figured it out yet, and we've been given the job, and we're going to look at it. So I'm going to have the equation of a circle. Now, do you notice that I'm not going to use numbers for the radius? I'm going to use the letter R. But isn't that the equation of a circle? Center of the origin, radius R. And if I draw just the top half of the shape, wouldn't that be negative R and wouldn't that be positive R? Do you agree? So if that was 49, it'd be 7 and minus 7, right? Now, if you take this guy here and you rotate him about the x-axis, don't you make a sphere? Right? Half a circle, x-axis, full sphere. If you rearrange this fella, you get that. And y then is the square root of this guy. So we know the volume. It's pi, the integral from start to finish of f of x squared dx. So far, so good. This is our f of x. It's going to be pi, the integral from negative r to r. Wait a minute. Squaring square roots is really nice, isn't squaring square roots? They cancel each other out. We are going to evaluate this integral at x equals -3, negative r, and finishing at x equals positive r. If I asked you to find the antiderivative of negative x squared, I hope you would just say power rule. Now, next one's a little bit trickier. I don't want you to think of r squared as some kind of power rule thing. I want you to think of r squared as 42 squared or 7 squared. Isn't it really just a number? R squared is a constant. It's just a number. So when you find the antiderivative for 42, it's 42x. And if it was 7, you'd get 7x. It's r squared. You get r squared x. Are you happy about the antiderivative of r squared is just r squared with an x? Because r and r squared are considered constants. Plug in r. You get r squared times r. Take away 1/3 r cubed. Subtract. Plug in negative r. R squared times negative r minus 1/3 negative r cubed. Okay, let's try and make this pretty. Those two get you r cubed, and that gets you, take away a third r cubed. This times this gets you negative r cubed, and this is negative r cubed, but that's also negative, so you end up with plus 1/3 r cubed. So far, so good? Right, let's see what that looks like. An r cubed, take away a third r cubed, take away is add an r cubed, take away 1/3 r cubed. That guy, that guy, that guy, and that guy are all r cubes, aren't they? So I've got 1, take away a third, that's 2/3. Add a 1, take away a third, that's add another 2/3. 4/3 r cubed, which is 4/3 pi r cubed. That's all it took to calculate the volume of a sphere. Now, somebody somewhere in the universe had to have done that the first time, right? It wasn't that somebody woke up from a sleep one day and said, oh, I think the volume of a sphere is 4/3 pi r cubed, and just got lucky, right? You know, that's not the way it happened. Didn't this have to be analysed and studied and figured out what it was? And now you have the same kind of tool. Couldn't you take any shape you like that you can deal with at least, rotate it about the x-axis and find the volume of that shape? What do you get if you take a straight line like y equals x, start it here, say finish here? If you rotate it about the x-axis, don't you get a cone? So we could find the volume of any cone in the world. And in a similar kind of way to I did this, we could generalize that and tell you the formula for every cone in the universe. And we could do it for ellipses. Do you know if you take an ellipse, which is basically the shape that looks like that, and you rotate it, don't you end up with a football-ish? We can find the volume of every football in the universe. Get a general formula for it or a specific formula. That is how powerful this technique is. As long as you can have it as a curve rotated about the x-axis, you can find its volume. As long as the f of x isn't ridiculously messy and big, right? As long as it's a relatively nice equation, you're good to go. Okay, say hi, everybody. This is a good point for us to finish. I know I've got one person who needs to stay behind. I think it's a homework question, but the rest of you who want to, feel free to do that. Otherwise, bye-bye. I'll see you tomorrow.
All right, thank you.
Thank you. Bye-bye.
You're welcome.
Goodbye.
We learned some cool stuff today, guys.
Thank you. Bye.
Thank you.
Right. I'll talk to my wife and find out, does she know Jack Hudson? Sure she does. Hi, Isabella. You are wanting to ask me some stuff?
Yeah, it was a
Not a
6.1
problem.
homework, number 11.
Is it a question you could read out loud to me, or shall I go in and find it? Is it how easy it is to write down?
I
Right.
could,
Kaylin, as soon as this is finished, we can have a quick chat.
I could probably tell it
Right.
to you.
What you got? Go for it. What does it say?
Okay, so the equations are y equals 4 cosine of 2x. And then the second one's y equals 4 minus 4 cosine of 2x.
Gotcha.
And then it's in between.
And is it the area between them?
Yeah.
Right. Have you tried Desmos on it? Did you draw a little sketch of it?
Yeah, I was able to get that. It's just finding the area I'm having trouble with.
Okay. So, while you're kind of ahead of the game here, I'm going to put in Desmos myself right now, because I need to get some numbers, and Desmos is going to be the guy that's going to help me get that. So I'll actually switch over so you can see what I'm typing, because some of what I'm doing is visual. Here we go. So I'm typing in the first function, which is that fella. Hit an enter. And then the other one is very similar, but it's got a 4. Take away this guy. Okay. I can tell from this picture that I don't need anywhere near as much of this. In fact, the area between them is this little guy here. Do you see it?
Well, for the second equation, it's 4 minus 4 cosine 2x. Like, yeah.
Oh, thank you. Right. Okay. Oh, it's pretty much the same idea, but just a bigger version, right? So what we have got here is a curve It curves down like this, and then it continues. And then I'll show you what I'm drawing in a few moments. And it curves up like that, and it continues. But before I go anywhere, do you see these two guys here?
Yeah.
Where the red curve meets up, these are intersection points. Do you see that guy there is negative pi upon 6? That's important. And the other one is positive pi upon 6. Do you see that? Right. The red one, which is this one here, is the 4 cosine 2x. And the blue one is the 4 minus 4 cosine 2x. Okay. Now returning, I'll actually show you pretty much what that said, and we can move from there. So that's like a baby version of what we have, right? So the area is this piece here. Well, if you want to find the area between them, it's from start to finish. So that's why I needed to know those. One of these guys is going to be f of x, and the other one's going to be g of x. And if I do my little baby rectangle thing, the highest up one is this fella. So he is going to be my f of x, right? This guy here, see him? He's my f of x. So that means this guy goes first. Take away the other one, he's going to be my g of x. So take away, put a bracket around it, this fella. Did you have that set up? Was that okay, or is that maybe where you went wrong?
Yeah, I had that set up.
Okay, that's good. So we're moving a little bit further on. This, take away that, what do you get? Well, you get 4 cosine 2x. Take away a negative means you add it. So I'm now going to have 8 cosine 2x's. Subtract 4. And now I'm going to find antiderivative. 8 cosine 2x. Right, we're going to do that linear shortcut thing. The antiderivative of cosine 2x is a half sine 2x. Right? And 8 times a half is why that's now 4 sine 2x. And the negative 4 gets you that guy. And I'm going to evaluate it from here to here. Are we good here, or is that where you went wrong?
We're good there.
We're good. Oh, we are nailing this. Right. So 4 sine. 2 lots of pi over 6 is pi over 3. Take away 4 lots of pi upon 6. That's the first one. Subtract 4 lots of 2. That guy is negative pi upon 3. And plug that guy in there, and essentially you get negative 4 negative pi over 6. Whoa, that's tight. Now squeeze that in. So I'm just rewriting this again. I've got this fella. That times that is negative 2/3 pi. Take away this guy. And take away this guy, makes that positive, but then you go and subtract it, so you end up with that fella. Okay, these two guys combine to get me 4/3 pi. I just need to find out what these fellas are, and we're done. What's the exact value for the sine of pi upon 3?
Root 3 over 2.
Yes, I was just checking. And this fella, what about negative? What's the sine of negative pi upon 3? If you imagine where it would be, it'd be down here, right in the 4th quadrant. So it has the same number.
Negative.
Yeah, but with a negative. So, oh, wait a minute. It's going to be 4 times that guy. Take away 4 times the negative of that guy. And I've already joined these two together. That's where that came from. And so it's going to be 4 times that gets me 2 root 3. Negative 4 times that is a positive, and they cancel. 2 root 3. Take away 4/3 pi. Phew. 4 root 3. Take away 4/3 pi.